A-level mechanics, Newton's laws, in particular, force equals mass times acceleration. Let's have a look at Newton's laws of motion. Originally, Newton was trying to explain the motion of the planets and the Sun relative to the Earth. Galileo had proposed the Sun should be taken as stationary, with the planets and Earth moving around it. There were other ideas at that time. Newton was trying to show which was correct. He came up with 3 laws of motion and 1 law of gravity, which he showed would accurately describe the motion of all astronomical bodies. These laws can be applied to any object. Now, none of these 3 laws are particularly complicated. They're fairly easy to understand. But what was interesting is that just these 3 laws, plus the law of gravity, was all that was needed to explain planetary motion. Now, the laws of motion are: the first law states a particle will remain in its same state of rest or uniform motion unless acted on by an external force. The second law states the acceleration of a body is proportional to the force acting on it and inversely proportional to its mass. And the third law states for every action, that is, for every force, there is an equal and opposite reaction. Now, the first law states that if there is no force acting on a body, it will either hang stationary in space or move in a straight line at constant speed. This was not so obvious. Everything on Earth is subject to the force of gravity, so the weightlessness of space was unfamiliar. But it is a necessary idea when explaining the motions of planets in space. On Earth, because of the presence of gravity, there is always at least one force acting on any body. However, the rule still applies on Earth if the resultant of all the forces acting on a body is 0. This also tells us that if a body is stationary, then the sum of all the forces acting on it is 0. This turns out to be very useful because on Earth many things, like buildings and bridges, are stationary. But we still want to find out what forces are acting on them so that we can work out how structurally strong they are. Now, the second law states the acceleration is proportional to the force acting on the body and inversely proportional to the mass of the body. Now, that's entirely reasonable. The harder you push something, the more you would expect it to accelerate. However, the larger the object, the harder it would be to make it accelerate. Now, we can rearrange that as the force is proportional to the mass times the acceleration of a body. And if we define a unit of force as the force needed to accelerate a mass of 1 unit with an acceleration of 1, then the force is equal to the mass times the acceleration. Now we define 1 Newton as the force needed to accelerate 1 kilogram with an acceleration of 1 meter per second squared. Then Newton's second law becomes F equals ma. This is a very important formula. The third law applies to 2 bodies. If there is a force acting on a body, then there's another body with an equal and opposite force acting on it. If an apple falls, it is because of the force of gravity from the Earth on the apple. However, there is an equal and opposite force of gravity from the apple on the Earth. However, since the mass of the apple is minute compared to the Earth, the acceleration of the Earth will be minute compared to the acceleration of the apple. This law states that for 2 objects in space, gravity would attract both bodies with equal and opposite forces. Although not part of the course, it's worth noting Newton's law of gravity. This is the last law that defines the motion of planets. Now, the law states that the gravitational force between 2 bodies with masses m1 and m2, a distance d apart, is proportional to m1 m2 over d squared. Or we can write that F equals g times m1 m2 over d squared, where g is a constant. Now g turns out to be 6.67408 times 10 to the minus 11 Newton meters squared per kilogram squared. From these four rules, Newton was able to calculate, with some very complicated maths, exactly where any heavenly body would be in the future from its currently observed motion. His results exactly agreed with the observations from the Royal Observatory, and so his work was accepted. Now the value of g was first found from an experiment by Henry Cavendish to calculate the mass of the Earth. It was found to be about 99% accurate, which was very good, as g is very, very small and therefore very difficult to measure. Let's have a review of forces. Now a force is a vector. This means it's got magnitude and direction. Now it's not possible to see a force, although it can be felt and its effects can be seen. If we hold a heavy object, we can feel its weight and we can feel the direction it's being pulled in. If we stretch a spring, we can feel the tension in the spring pulling back against us. Not being able to see the forces sometimes makes it difficult to imagine and draw in all the forces in a given situation. But it's very important that we get our diagrams right. If one or more of the forces are overlooked and left out, it may not be possible to solve a problem. If we consider a body under some forces, there will be external forces acting from outside and internal forces contained within the body. We can usually ignore the internal forces if we are considering the motion of the body. For example, if we consider a car pulling a caravan, then if we consider them separately, the tension in the tow bar is an external force on each of them. However, if we consider the car and caravan as a single body, we can ignore the tension in the tow bar. This is now an internal force. When considering a problem involving forces, it is always important to draw a diagram and mark the forces in. Let's have a look at some common types of forces. Now the first one is weight. The weight of an object is the force vertically down caused by the gravitational attraction of the Earth. If a mass of m kilograms is released, it will fall with an acceleration of g meters per second squared, where g is 9.8. So the force on it is mg newtons. So the weight of an object is g times its mass. Now weight is measured in newtons, mass is measured in kilograms. The mass of an object is fixed, but its weight may vary. For example, the weight of an object on the moon will be a lot less than its weight on Earth. Another force is the normal reaction. When two objects are pressed together, they push against each other. This force is perpendicular or normal to the surfaces. For example, an object resting on flat ground will have a vertical force acting upwards on it. Then we have friction. When two objects are in contact, there is often a force preventing them slipping across each other. This is called friction and acts along the surface of contact. The normal reaction and the friction will always be perpendicular to each other. A surface is said to be smooth if it has no friction when in contact with another object. Actually, there'll always be some friction, but we say the surface is smooth if the frictional force is so small it can be ignored. Some surfaces, such as ice, have some but very little friction, so it's very easy to slide. Resistance. Friction is one form of resistance. Any force that acts to prevent an object moving is called resistance. Another example is air resistance. resistance always acts in the opposite direction to the attempted motion. Then we have tension. If an object is connected to a string and the string is pulled taut, the object will experience a force caused by and in the direction of the string. This is called tension and is always away from the object. Similarly, we have thrust. If a rod or a spring pushes against an object, the object will feel a force acting along the direction of the rod or spring. This force always acts towards the object and is called the thrust. Let's look at a couple of examples. A body suspended by a string from a beam will have two forces acting on it, its weight and the tension in the string. A body resting on a plane will have three forces acting on it, its weight, the normal reaction, and friction. Let's have a look at an example. Example 1. A car of mass 850 kilograms accelerates from rest. It has a constant driving force of 1,500 newtons and a resistance to motion of 225 newtons. In part A, we're asked to calculate its acceleration. Well, to solve this, the first thing to do is draw a diagram and mark in the forces. There's the driving force, which is forward, 1,500 newtons. There's the resistance, which is backwards, 225 newtons. There's the weight, which is 850 G down, and there's the normal reaction, which is up. If we resolve horizontally and use F equals ma, we have 1,500 minus 225 equals 850A. So 850A is equal to 1,275, and if we divide by 850, we get A is equal to 1.5. So the acceleration is 1.5 meters per second squared. In part B, we're asked how long does it take to cover a distance of 192 meters. Well, we have U is equal to 0, A is equal to 1.5, S is equal to 192, and we're trying to work out T. So, using S equals UT plus a half AT squared, we have 192 equals 0 plus a half times 1.5 T squared. In other words, 0.75 T squared is equal to 192. Now if we divide both sides by 0.75, we get T squared is equal to 256. And then if we take the square root, we get T is equal to 16. So it takes 16 seconds to cover a distance of 192 meters. In example 2, a model truck of mass 0.5 kg is released from rest on a slope of 25 degrees with the horizontal. Assuming the resistance to motion is negligible, in part A we're asked to draw a diagram of the forces acting on the truck. So we can draw the diagram and mark in the forces. Now there's a gravitational force of 0.5 g acting vertically downwards and a normal reaction acting at right angles to the slope. In part B, we're asked to calculate the acceleration down the slope. So we use F equals ma to resolve down the slope. To resolve in a given direction, we take the force and multiply by the cosine of the angle between the slope and the direction of the force. This angle is 65 degrees. So we have 0.5 g cosine 65 degrees is equal to 0.5a. In other words, a is equal to g cosine 65 degrees, and that turns out to be a is 4.14165. So the acceleration is 4.14 meters per second squared. And then in part C we're asked, how far does it travel in 3 seconds? Well, we've got A is equal to 4.14165. We've got the initial speed u is 0. The time is 3. And we're trying to find out how far it travels. That's s. So using s equals ut plus a half at squared, we've got s is equal to 0 plus 0.5 times 4.14165 times 3 squared, which is 18.637. So the distance it'll cover is 18.6 metres. Let's look at one more example, example 3. A woman stands in a stationary lift holding a parcel case of mass 5 kg. In part A, we're asked to find the tension in the handle of the case. Well, to solve this, draw a diagram of the case and mark in the forces. There is the weight of the case down, that is 5g, and the tension up. Since there's no acceleration, we have t equals 5g, so t is equal to 5 times 9.8, which is 49 newtons. So our answer is the tension is 49 newtons. The lift then starts moving up with an acceleration of 2.4 meters per second squared. In part B, we're asked to find the tension now in the case's handle. While the lift has an acceleration of 2.4 meters per second squared, we can draw the diagram and then resolve upwards using F equals ma. There is a weight down, that's 5g, and a tension up, we can call that t. Now there's an acceleration of 2.4 meters per second squared up. And so we have t minus 5g is equal to 5 times 2.4, or t minus 49 equals 120, and so t is 169. So the tension now will be 169 newtons. The lift then moves at a steady speed. In part C, we're asked, what is the tension now? Well, while the lift is moving at a steady speed, the case would have no acceleration, and so the situation would be the same as in part A. So the tension would be 49 newtons. Before reaching the top, the lift decelerates at 4.2 meters per second squared. In part D, we're asked, what is the tension in the case's handle now? In the final stage, the lift has a deceleration of 4.2. So we can draw a diagram and then resolve upwards using F equals ma. Now there's a weight downwards of 5g and a tension upwards we can call t. Also, there's a deceleration of 4.2, which means there's a negative acceleration of 4.2 upwards. So we have t minus 5g equals minus 4.2 times 5. So t equals 49 minus 21, which is 28. So in the final stage, the tension in the handle is 28 newtons.